Hello, welcome to the third video to accompany the Further Maths Conference Complex Numbers session. In this video, we're going to explore a way of visualising complex numbers that again draws heavily on ideas that will be familiar to your students from GCSE or even earlier. How can we measure the size of a complex number? If you've not thought about this before, pause the video while you have a think now. What difficulties arise? I wonder what ideas you came up with. One way to think about the size of complex numbers is to plot them as points on a coordinate grid. The diagram we use is called an Argand diagram, but it's really no more than a standard coordinate grid. The real part of the number is represented on the x-axis and the imaginary part on the y. So this is just some Year 6 work repackaged. Oh, and here's another opportunity to throw in some history or suggest some research for your students. Who was Argand, and why is this diagram named after him? So, what about the size of these numbers? Well, we can consider how far away the point is from the origin, or, if you prefer, the length of the associated vector. This is called the modulus of the complex number, and of course we use Pythagoras to work it out. This is where students need to be careful with that definition we had earlier about real and imaginary parts. Remember that y is a real number. Don't let them square yi and end up with a subtraction in there. One way to avoid this is to make plenty of use of diagrams and encourage students just to apply what they already know and are confident with, rather than relying on formulae. If your students are already familiar with the modulus function in real numbers, it's worth pausing to note that if the imaginary part of z is 0, in other words, if your number is actually real, then this corresponds with the real number modulus function. If they haven't met it yet, you can save this for when they do. Pause the video while you have a quick go at these. Where are your students going to go wrong? OK, my experience is that students get in a twist with the minus signs. I relate to this, as losing minus signs is probably my own most common error. But if they are thinking visually about these numbers, then the minus signs don't need to come in at all. So for B, if they think 5 minus 12i, and this right-angled triangle, then there isn't a problem at all. Of course, these are all nice Pythagorean triples, so 3, 4, 5, 5, 12, 13, 6, 8, 10, 10, 24, 26. One of the downsides of the demise of coursework at GCSE is that students are less likely to be familiar with the world of Pythagorean triples. Can you make time in Key Stage 4 to do a brief investigation? It's useful for ordinary A-level students, as well as further mathematicians. Now let's look at the angle theta that the line makes with the positive real axis. So, here I've got the complex number x plus iy. I formed a right-angled triangle with base x and height y. R is the hypotenuse, and it's also the modulus that we defined just now, the distance from the origin. I've marked the angle theta that the line makes with the positive real axis. This is called the argument of the complex number. Just a word of warning here. This angle is measured in radians, and with the 2017 specifications, radians are not covered at all in AS Mathematics. This means that if you are teaching further maths in parallel with maths, your students won't be meeting radians elsewhere, so you'll have to introduce it here. And this angle is measured anti-clockwise from the positive real axis. Calculating the argument is straightforward trigonometry. If they've met the inverse trig functions formally, then use arctan here. If not, have a think about whether introducing the correct language here will save time in the long run, or whether it's better to keep it simple. Again, this is just GCSE content in a new context. So far, we have plotted the position of a complex number on the Argand diagram by going horizontally on the real axis and vertically on the imaginary. This is just like plotting coordinates on x-y axes. But you can also use modulus argument form to define position, which is just polar coordinates, which students will meet in the second year of further maths. So there are opportunities to make links forwards into future content to whet their appetites, as well as back to material they've already met. So, we've covered quite a lot of content, and hopefully you've seen that most of it is just GCSE content with a slight twist, making it an excellent choice of topic for starting Year 12. New, quirky, but not really difficult, and with no dependence at all on material from A-level maths. The final video has an idea for an enrichment activity involving complex numbers.